I'm not Asif, I'm Keshav Murthy. I manage the R&D within Couchbase. So we have talked over a number of sessions. We have covered the motivations, the language details of Nickel. In this session, we'll talk about optimization, right? What type of indexes do we have? How do we optimize the query? How do you optimize the Nickel query? That's the main focus, right? I'll have a very brief introduction, a reintroduction of Nickel, followed by a few minutes on how to understand the query plan, right? When you have, when somebody comes to you and says, my query is running slow, what are the questions to ask, right? So we'll talk about that. And I'll talk about how does the Nickel optimizer come up with a query plan, right? What does it do? So we'll talk about that, and then query and indexing features. In the next 40 minutes, I have to cover all the details that we have in the 400-page book. So I will not try to do that. But if you haven't taken the book already, which has gory details of what I'm going to talk about in the next 40 minutes, we have some additional books in Expo booth. Please pick it up from there. Okay. What does a SQL engine do? It takes sets of relations as input. Based on the query that you have given, it processes the process the data that is coming in, and then the result of the query is another relation or another set of tuples. In NoSQL systems, if you have input as sets of JSON documents without a declarative query language, you have to write the application logic to fetch the documents that you're interested in, do the processing, and give the result back. And that's built manually and expensive. What we are trying to do is give you the steering wheel back that you can manipulate the data in a very flexible manner to achieve your business objective. Right? This is what is the goal of Nickel. Input is sets of JSON documents. Result is a set of JSON documents. Right? You don't lose any structure. You have the full flexibility of JSON as input as well as output. Right? This is the goal of Nickel. Give developers and enterprises an expressive, powerful, and a complete language for querying, transforming, and manipulating JSON data. Okay? So take a look at this query. This query looks and feels like SQL, and that's by design. I'll highlight a few differences. For example, in the projection list, we have an aggregate on order line. Order line is something that is projected from the unnest operation. JSON, in the previous talk, I talked about the unnest operation. Unnest operation helps you to flatten the arrays. So once you have the arrays flattened, you can process them just like any relational tuple, and you can do the standard filtering and aggregation on those as well. So unnest, we support unnest nest to manage the array data, as well as we support inner joins and left outer joins in Nickel. In terms of aggregation, both in the aggregation and group by is supported. That works and looks and works just like SQL. And having clause again helps you to filter out after the aggregation just like SQL, and followed by order by. We support the limit and the offset for your pagination queries as well. So while this example is SQL, Nickel is a full-fledged query language with support for insert, update, delete, merge, in addition to select as well. Okay, so since this is a talk on optimization, let's focus on the infrastructure that we have that the optimizer uses to come up with a query plan and execute your query. Right? The core of the infrastructure is the index. So in terms of the index, we have I have gone to very granular level, but at the high level, we have these 9 different types of index. I'll come back to this later in the talk. right? The primary index, whether it's simple primary index or named primary index, is roughly equivalent to your table scans. It's very good when you are developing applications, you're developing your queries. Every query can be run using a primary index. So, but in production, it's optional to have the primary index because you don't want to be surprised by a query that uses the primary scan. Second index scan, whether it's a simple key or a composite key, is supported as well as functional index. For example, when you want to have a case-insensitive search, you can upper or lower the value before you index on it, and you can issue queries that does a case-insensitive search of the search or scan of the data. Array indexing helps you to index individual elements of an array. Array can have scalar values or objects or arrays of arrays. The array indexing functionality in Couchbase helps you to index only the scalar values that you need within a complex array. Partial index help you to create indexes on a subset of the data. Covering index is optimized addition. We evaluate all the indexes to see if an index can completely cover the query. That means, does the index has enough data or all the data to answer your query? So that's a covering index. Duplicate index or the replica, or we call the replica index now, is a mechanism where you can have multiple indices with the same signature. That means this is done both for high availability as well as load balancing. If there are multiple indexes with the same keys, we can load balance here as well. So those are the different types of indexes that you have available. Let's look at, given given sets of indices for your query and the query, how do we come up with a query plan, and how does the query actually run, right? So eventually, the goal of the optimizer is to come up with a query plan that executes efficiently. Let's look at how the query actually executes. The applications issue the query over REST, whether you issue directly or through any of the SDKs. Eventually, the query request from the application comes to the query service over REST. The query service, and as you can see that multiple layers here, there can be multiple query services, multiple index services, multiple data services. This is the whole Couchbase cluster. The query service which gets this particular request analyzes the query, does the parsing, semantic analysis, and then query service comes up with the actual query plan, right? That's where the optimization happens. We'll get into that more in a moment. Once it comes up with the query plan, if the query requires index scans, it will go ahead and request the index service to do the scan. Again, the request for each index, we go to one index service. There can be multiple index services, there can be multiple indices, but each of the index scan requests go to a particular scan. A single query can use multiple indices, and that request can go to multiple index services, but each index scan goes to a single index service. As the index service returns us the list of qualified documents, right? The whole idea of using the index is to reduce the amount of data that we process, right? It does apply the predicates and gives us the first level of qualified documents, and as the document keys coming in, we go and get the document from the data service, and it's all done in a streaming fashion, so it does work in parallel. Once the data comes back to the query service, we do the further processing. There are always predicates that we could not push down to the index service. We do the post fetch predicate evaluation, as well as joins, pre-aggregation, aggregation, sorting, pagination, all that happens within the query service as well before we finalize the result and send it back to the application, right? This is the whole loop from the query request back to the result, right? This is a little bit of the inside view of how the query service works. from the parse to planning to scans to fetch. So each of the phases are executed serially. Whenever the scans and fetch and the joins have to get the data from index service or the data service, they do that. And you see there are some blocks that are single blocks. There are several phases that are multiple blocks. When you see multiple blocks, these phases can be parallelized. Scans, fetch, joins can be parallelized, whereas parsing and planning is a serial operation. So we can divide this execution into three phases: the prepare phase, the run phase, and the final projection phase. When you have applications where the same query with different bind values are running millions of times, you can prepare the query once and execute it multiple times, so you save the time that is taken for prepare. Right? Sometimes the prepare can take few, depending on the complexity of your query, depending on the number of access paths. That means number of indices that you have. It can take a few milliseconds to tens of milliseconds. You can save the time on the prepare time for each subsequent execution by preparing and just simply executing with different bind values. Right? Okay, so let's get into the details of the query planning phase, right? So each query, right, logically, the purpose of declarative query language is the application tells this is what I want to do. How it is done is decided by the optimizer, right? So, and each query can be executed in several ways, whether we can do every query can be run using primary index, and that's not the most efficient. That's why we have all these different types of indexes. We have to choose the access path. That means, are we using a particular index? Are we doing primary scan? Are we doing a key scan? We have to choose the access path for each key space. And once we decide on the index, we have to decide what predicates, what filters have to be pushed down for each index. What should be pushed down? What should be what filters has to be processed post fetch? We have to we have determined the join order and join method. In case of nickel, at this moment it's a little bit easier because we do the join order from left to right as specified within your query. And right now we implement only the nested loop join, so that's a pretty straightforward thing. Once all these decisions are made, we create the execution tree that gets executed eventually. Your query plan essentially is represented by this query execution tree. Right? For each query, like I said, we have to evaluate the different indices and decide which index is most appropriate. I'll share the rules with you. Right now, this evaluation and selection is done by rule-based engine, not a cost-based engine. Right? We just know the sets of indices that are available. We have rules that I'll share with you later on. Based on the rule, we select one or more indices for the query. It's not cost-based yet. And then we evaluate the query and the index that is chosen to see whether this index has all the data that is required to answer your query. If it does, then it's a covering index. We avoid going and fetching the data from the KV altogether. That's a performance optimization. And then create the index filters, post scan and post join filters, and projection optimization. Okay. Understanding the query plan. Okay. So this alone requires a pretty detailed talk. I'll cover this briefly, but there is a detailed article in our book as well as on the D-Zone, which explains this understanding the query plan in gory detail. And for the people who are working with databases in general and nickel as well, it's very important to spend some time to understand how to understand the query plan. Because when somebody comes to you and says, my query is slow first thing we ask is, oh, it's slow, show me your plan, right? Has it chosen the right index? Has it pushed down the right predicates? Has it done the, is it possible to do the covering here? There are standards of questions we ask, but the key to it is looking at the plan. Plan tells you how the query is getting executed. Right? So let's look at the details of this query plan. Right? In this query plan, I have a index on travel sample, and I have a query that has three predicates. Yes, type equals airline, country equals United States, ID between 10 and 100, and then I have order by on country comma ID followed by offset 5 and limit 10. In this case, we have a index that can cover. If the index can cover, you see the attribute in the plan on your left hand side. The covers tells you whether the index is able to cover this query or not. Right? That means we don't have to go to the data, so it's we just do less work. Right? This is one of the goals of optimization. Right? Every optimizer tries to come up with a plan that does least amount of work. Right? We want to be as lazy as possible, because that means you have resources available for multiple concurrent queries. The second thing to note is filter covers. In this index, it's what we call as a parser index. Basically, this index has a type equals airline, so there's a match of the weight loss as well. If you do project type, we can just simply see, because it's an equality predicate, we know every type here has to be airline, and that's covered by the index as well. So we print the index name. So it's important to see that for the query, does it pick up the index that we expect? Next is the key space. There's a key space that you have specified in your query. And then there is a key called limit. Here, because the index is able to cover the whole query, we can push the limit and the offset to the index. Right? Here we have said offset 5, limit 10. So we push 5 plus 10 to the index. What's happening here is the query is only interested in the 10 documents, but we are not interested in the first 5 documents. We are interested in the 6th to 15th. What we do, this is a Couchbase 4.5 plan. We tell the index, okay, we are interested in the 15 documents, and we get the 15 documents. We ignore the first 5 and then give you the 10 back. Right? In 5.0, we have done the optimization. We have done this enhancement where we can push down limit as well as the offset. So the indexer itself, if you have for the same query in 5.0, it will paginate and ignore the first 5. Basically, it does the offset of first 5 and gives back only the 10 documents we are interested in. When the offset is 5, it's not a huge difference. We have customers where there is offset 8,000. We even had a customer in the forum. We have done some optimizations when usually paginate, even Google, when you do next. How many of you have done next in Google until it no longer gives you the result? What's the limit on Google? Sometimes it's 256, sometimes it goes up to 1,000 if it's interested. If you search for Apple, for example, there are 10 billion documents that is specified. For pagination, it doesn't allow you more than 1,000. That's what I have seen. But in enterprise database systems, we can't say after offset 1,000, no, we don't have any data, I will give you an error. You can't say that in a database system. You have to give the answer if you have the data, right? No matter what the performance implication is. So here, we had a customer in the forum who said, offset 1 million. I did ask, what is your use case? I didn't get a reply, but there are very interesting use cases. They do that as well. So when there are big offsets, then indexer just skipping over the data that you're not interested in makes it resource efficient. So, we have done that optimization in 5.0, and the whole purpose of explaining this is you can look at this information in the explain to understand how the query is getting executed. So far, I talked about the non-predicate attributes. That means all the limit, whether we have covered or not. The next thing is a section called spans, right? Spans represent the predicates that we have pushed down through the index scan, right? Like I mentioned earlier, the index is used to reduce the amount of data that we do the fetch, we do the further processing, and index has to know what is the filter that it has to work on, what are we interested in, right? And spans represent what we are telling it to do, right? So if you see here, we have three predicates: type equals airline, country equals United States, ID between 10 and 1000, and here we have only two predicates with country equals United States and ID between 10 and 1000. Where did the third predicate go? Anybody wants to try the answer? It says index is covered. Index can handle all your data. We have three predicates, but we have pushed down only two predicates. What happened to the third predicate? Okay. If you see the index definition, index has a where type equals airline, right? So that tells us index only contains airline data. So when you have a query that has type equals airline, you say, oh, this index only contains the data that for airline, and that's not a key. The spans contain the filters on index keys. And if you look up the filter covers key above the spans, that has got this filter cover t.type equals airline, right? We have that where clause covers it. That means the index contains only airline. There is no processing to be, there is no additional processing to be done for airline, right? So it's important to understand the spans, because spans represent what the index scan is actually doing, right? That's when we say the low and high value, that's the range of values that index will process and return to us. Okay? Yeah, good point. Inclusion is when you have, it says whether to include the low value or to include the high value, or include both, or include nothing, right? So that's a good point as well. Okay. So we talked about predicate push down. So a lot of the improvements for predicate push down has been done in 4.5. Not only we push down the predicate, push down the limit, and now the offset. If we see that the order by clause in your query matches the index key ordering, index organizes its data based on the ordered set of keys. So we fetch the data from the index in that order. So again, we can avoid the sorting after we fetch the data. Okay. So for that, the index in this case, you have an index called country comma ID, and you have the order by dot country comma ID. So there is a match. So we can avoid the sorting altogether as well. This is again the purpose of optimizer is to find the access paths where you can minimize the amount of data that is processed as well. The second benefit of this pushing down the order by to the index ordering is, a lot of times you want to do the ordering, but you're only interested in the first 5 values, or the 100 values past offset, in this case offset 5 and limit 10. If we can't push down the order by to the index. We have to fetch the complete result, potentially complete result, do the sorting, and then give you the 5 or 10 values that you're interested in, right? It's important to understand the effect of index key ordering for order by as well as pagination. So having the right index where we can push down our predicates, our order by, as well as the pagination clause, the limit and the offset, will help you to run your query and the application as fast as possible, right? So we discussed the general query processing. Let's see how the covering index works. When you have a query that can be completely addressed by your index, the optimizer within the query service creates a plan that avoids going to the data. It's simply goes to the index service, gets the answers back, and does the post processing within the query service and gets your result back. The data service doesn't even come into play to answer your query. This is called the covering index, and the query is called the covered query. One of the things that we have done in 5.0 is, again, this is a resource optimization. You could have an index with 10 different keys, right? But your query may be only interested in 3 different keys, right? So when it is covered, we ask the optimizer to project only the required values. So that means if you have 10 values, the optimizer only returns the 3 values that you're interested in, and for that, optimizer only projects the 3 values you're interested in, and so the amount of data that is exchanged between the index service and the data service is reduced. That's a performance optimization. Now, when you have a query that is not covered, then that means part of the query predicates is pushed down to the index, and index does the index scan based on the predicate, gives you the intermediate results, and then query will go and fetch the data from the data service, and then it does the post processing. If you see the filter condition, the filter operator within the query plan, that has additional processing that has to be done by the query engine before we get the results back to the application. If you do have a index that covers your query, that means you have a composite index that covers multiple predicates in your query, that's fine and good. Sometimes if you have indexes that covers different parts of your where clause, for different predicates, we evaluate that situation, and we can use multiple indexes for the same query, and we do the intersection of that. We have a bitmap layer sitting on top of our parallel scan layer that can exploit multiple indexes for the same query and returns the results back to you. So sometimes if you have, when you have composite indexes, the order of the indexes is very important, right? And if you have a composite index with 10 keys, if you have a predicate on first key, the 5th key, and the 10th key, we only push the predicate on the first key, the first n keys, right? If it is 1 and 2, that's fine. First 1 and 2 is fine. The index cannot process predicates if you skip over any of the values. So then sometimes you'll end up with creating indices for different, like if you have 10 values, all the combinations return in like 10 factorial, there's like 3,000 indexes or something, right? So, and depending on the number of keys, number of indexes can increase. So intersect scan helps you to reduce this explosion in number of indexes, but you do have to remember it is a little bit more expensive in the sense we have multiple predicates. One predicate could be a high selectivity predicate, so then it will use more resources, but it will reduce the amount of index maintenance for you. In 4.5, we introduce a new type of index called array indexing. So if you have an array within your JSON document, I mentioned in the previous talk that JSON gives you flexibility, right? Flexibility in terms of the basic structure. You can you don't have to have all the key value pairs. You can add new key value pairs without trying to do any alters. But there is additional flexibility in terms of objects. You can have objects within JSON document. You can also have arrays. And arrays and combination of arrays of objects of arrays and multiple nested level is what gives you the most power within JSON, right? You have when you have to plan for number of hobbies for a customer, a number of services that they're using from your organization for a customer. You don't have to decide ahead of time whether it is 3 or 4 or 10. You just put an array and it can grow and without breaking an application. But you do need to understand how you efficiently process the arrays, and array indexing is one such method. And any predicate that you use in the select statement, any v in schedule satisfies v dot day in 1, 2. That's how you evaluate whether an array contains a particular value that you have. This satisfies clause, the expression, the Boolean expression that follows the satisfies clause is flexible. You can give any Boolean expression that you use in a where clause after the satisfies class, but it has to be surrounded by this any syntax. Then the key thing is having the ability to push down this predicate into the into your index, and for that you need to create an index on individual elements. And this is the syntax. It's not, once you get used to it, it's pretty straightforward. So in here we are creating an index on v dot day in the schedule, right? So once you do that, you see on the left hand side for the query, you remember the discussion we had on the spans, right? Spans represent the filters that we are pushing down to the index scan. In this case, for the spans has 2 ranges. One range is start from 1 to 1, second range is 1 to 2. That spans information in your query plan represents v dot day in 1, 2, right? So we can export the index, array index for your indexing as well. Yeah, count scan is optimization for the count when it is covered. So it's a simple optimization of the aggregate. And when you have joins, left out join and inner join, we choose the index for the first key space, right? You always join from your child to the parent. You need to have reference from your child to the parent. So the rest of the key spaces are accessed directly using the key value. For the first key space, we use the index. That's where all the index selection is made. Yeah. So if you look in, when you see the actual explain plan, you'll see what we have, what index has been chosen for the first key space, and how the what predicates have been pushed down for this. In this case, for example, I'm doing a join from travel sample R. That's a route to the travel for the second one. Yeah, second one I'm doing a key lookup based on the airline ID. That's the A represents the airlines, and then I have a predicate for the route, right? Predicate for the route as well as the schedule, and we can use any kind of index for the first key space, and then once you minimize the amount of data set based on the index scan, and everything else becomes a lookup. We also have not only you can do you can represent both parent to child, child to parent relationship. So that means if you start with a child which has a pointer to the parent, you say orders, which is a pointer to the customer, orders join customer on keys orders dot customer ID. You can, if you do choose to have the child document ID in the parent, you can start with the parent. In this case, I'm starting with brewery, which doesn't have all the keys for the beer, but okay, let me look at it. In this case, I'm starting with brewery. I'm pushing down the predicate state equals California into the first scan, followed by, now I get the reference to the actual state, which is the key, as well as the document ID of the brewery. Instead of looking up directly as a key value, there is an index on brewery ID. I look it up, and then it's a two-step process. Instead of looking up, doing a join directly to the parent document, I look up through the index. It's a performance optimization where you can have the list of children IDs in the parent instead of child pointing to the parent. What this plan says is covering index in 4.5. We could do the full covering index only when you had either full complete scan of a single key space, or an inner join, or a left outer join. Now, even when you have this for join with a left outer join, right? Even when you have parents keeping parent document containing the list of child documents, even then we can do the covering scan without having to go and fetch the data from the child. Yeah, so covering is again extended to multiple use cases, whether it is a simple join or an index join. This is showing the explained plan for the index join. We have done the optimization for the aggregation. So this is how a simple aggregation works, right? When you have aggregation, first we do the group by, and then do the intermediate aggregation, followed by the final aggregation. When you this is the final set of phases: sort, offset, and limit. Sort is the sort order is determined by the order by clause. Without the specification of the ascending and descending modifier. By default, it is ascending. The index is stored in the ascending, and the scan is done in the ascending order as well. In 5.0, you can create indices where keys are either stored in ascending order or descending order. You can have any combination of ascending and descending order, and when the order by matches the index ordering, right, ascending and descending, we can simply exploit the index order without having to sort. And like I said earlier, by using the order by that is in the index order, your pagination queries, the offset and the limits, work very well. And final phase is the projection phase, where we project the final values in this. I am running out of time a little bit. Like I said, we have a lot more details in the book, and this book is available as a PDF in our blog as well. But I'll give you a brief overview of where we are. We are a rule-based optimizer. First, we choose the index, followed by choose the index for the first key space in the from clause, and then we do the optimization for each query block separately. We don't do the subquery flattening or query rewrite. We simply optimize each of the query blocks, right? In terms of the index selection, if the query contains use keys, we use the use keys. If the query if the query does not contain use case, depending on the predicate, we prefer the covering scans over non-covering scans. We try to use the index that can cover all of your predicates. If you have if you have 3 predicates, but you have indexes on just one of the predicate or 2 predicates, or composite index on 3 of the keys, we prefer the widest index that can cover your queries. Then we evaluate it to see whether the query can be covered by this index or not. If none of the indexes satisfy our evaluation or satisfy your query, the fallback is the primary index. That's why primary index is good to have during your development. In production, you don't want unexpected queries to be taking a lot of resources, so having the primary scan is optional. Okay, so we choose the indexes that are online, and when we are still a rule-based optimizer, and sometimes the data skew can result in a non-optimal query plan. So if you do know what is the right query plan, you can change the index that is chosen by using the use index. Use index, you can give 1 or more indices. So it's either a single scan or a intersect scan. Right? We choose the index. We first evaluate whether the where clause, whether the predicates that you have given is a subset of the where clause in the create index statement, and then the index scan has to match as well. So in the interest of time here, let me okay. So this is the final query tuning checklist. I'll go through this before I wrap up. The first thing is avoid primary index scan, right? That's the number 1 rule. And try to create the indexes, composite indexes that satisfy your query. And if possible, if you can, you can horizontally partition the index into multiple indexes by using the where clause in the index, so you have your index, the index that is appropriate for your query. And try to create the index with all the values that you need in your query. That means not only the predicate, if you have additional columns that are in the query, so that the query can be completely covered. That means we can avoid get the whole data into the query service and do post processing, right? So this is the kind of the trade-off between amount of data that you have to save in your index versus amount of fetch you need to do. If the document size is reasonable, it's not a big deal. If the document size is multiple megabytes, getting all the documents does take network memory traffic. If the index number of indexes does become unwieldy, explore the intersect scans. So the intersect scan itself, its performance has improved dramatically in 4.6.2 as well as 5.0. When you have arrays, you do need to use the array indexes. Array indexes can index not just at the top level, it can index the specific elements that you're interested in at any depth of the array structure. Yeah, and when you need to fetch directly using use keys, you not only can fetch a single document, you can give an array of values, you can fetch all of them quite quickly. If you're using 4, 5, 1 or above, setting the pretty equals false as a query parameter will improve the performance as well. When you have, by default, the max parallelism for the query is 1. That means a lot of the phases, the scan, the join phase, the aggregation phase is all single-threaded. The data fetch is always parallel no matter what parallelism you set. So if you have expensive queries, increase the max parallelism for those queries to parallelize them as well. If you have a query that does need to fetch lot of data from your system, the default, number of documents we set, we start with 16. If you still have more documents pending for the query, we go up to 512 document fetch at a time. That's the default setting. You can change these settings to higher level if your query is fetching more than 512 documents for each query, right? And of course, after you tried all this, if you're still hitting the limits, you will have to end up doing adding new query nodes and index nodes. This can be done online, and your applications can scale. Right? So we write a lot of articles on dzone, and like I mentioned, we have much more detailed stepwise details in the book as well. One of the things that we have done both in the articles and in the book is all the examples are from travel sample. You can actually cut and paste and see these queries working, how they work, so you can get the experience. You don't have to understand the theory and translate everything, so it's already translated for you. That's my last slide. Thank you very much.